session. I'm not sure what that exactly means, but it means everyone's supposed to sit up straight in their chairs, as near as I can tell. The first speaker this morning is Yi-Wan Lee from the Institute of Atmospheric Physics. And she's going to talk on orthogonal curvilinear terrain following coordinate for atmospheric models.
Thank you very much for the introduction. And
again, I'm going to introduce an orthogonal curvilinear terrain following coordinate for the atmospheric model. There are four parts. One, the motivation, and then the orthogonal terrain following coordinate. After that is the idealized experiment. Finally, the conclusion. First, we're going to talk about the motivation. Although most of the speakers in this vertical session seems to come from Asia, but the surface of the Earth is complex all over the world. And we do our simulation on the Earth for the geophysical flow, so we have the complex lower boundary for the numeric model. And the carefully chosen of the vertical coordinate can simplify the lower boundary. So the choice of the vertical coordinate system is the most important aspect of designing a model. Let's have a look at the common chosen of the vertical coordinate and its limitations. Until now, most atmospheric model and oceanic model use the terrain following coordinate. There are two kinds. First one is pressure-based sigma coordinate, originated by the Phillips. They use pressure P to design the sigma. And the other one is height-based sigma coordinate. In their definition, they use the height z to define the sigma. And both this kind are non-orthogonal coordinate because the basis vectors of the coordinate is non-orthogonal. There are two well-known computational errors in the sigma coordinate. First one is the errors of the advection, and the second one is the error of pressure gradient force. I want to show a little bit more details where these two errors come from, because later on in my new coordinate, we're going to show how to avoid them. For the PGF errors, the expression of the PGF in the sigma coordinate is these two terms. And these two terms always have the same order of magnitude and opposite in sign, which induce the PGF errors. And for the advection errors, when we calculate the horizontal advection in the sigma coordinate, we actually calculate it along the steep sigma levels, which induce the advection errors. And now, there are numbers of methods proposed to overcome these errors. For the PGF errors, in general, there are two kinds of methods. First one is upon the two-term computational form. People propose methods to alleviate the errors to an acceptable level. Alternatively, we have a one-term computational form of PGF method can do this in a sigma coordinate and bypass the errors. However, in this method, here's the example of the equation in it. There are additional terms in this method associated with the non-orthogonal characteristics of the classic coordinate. So, note that all these methods are doing their effort still in the non-orthogonal sigma coordinate. On the other hand, to the advection errors, we always propose a method to decrease the slope of the sigma level. So to overcome these errors. For example, the familiar in every model is the hybrid coordinate. Here we can see these two significant errors in the sigma coordinate is solved separately. Wouldn't it be great if both can be killed by one stone? Let's find this stone. Let's see the momentum equation in the z coordinate. Here is the horizontal momentum equation again. And we can see that the PGF in the z coordinate is one term, so there's no PGF errors. And there's non-curvilinear terms in this equation. Why this equation is so simple in the z coordinate? Because the z coordinate is an orthogonal one. So we design an orthogonal terrain following coordinate. And in the designing, we consider the advection errors in the design. So we can find this stone. Well, we're going to introduce the orthogonal sigma coordinate. First, how to do this. And in the design of a terrain following coordinate, there are three key aspects. First one is the boundary condition. All we have to do is to turn the terrain into a sigma level. And the other two is the definition of the coordinate as the basis vectors. In the design of the classic sigma coordinate, they do things in this way. They define the coordinate first, like the Phillips do. They do the pressure and define the sigma coordinate, and then use the definition to resolve the basis vectors. We have done this in another way around. Firstly, we resolve the basis vectors of the coordinate and then the definition of it. How to do that? We rotate the z-coordinate, basis vectors of the z-coordinate, as shown in the black arrow, until the vertical direction in line with the normal vector of the terrain, the green pairs. And then we got the terrain following and orthogonal basis vectors. Use the expression of the basis vectors in a curvilinear coordinate. We can solve the coordinate transformation between the z-coordinate and the rotated one. Here is all the thought behind the new coordinate. And we do it in 3D because our atmospheric motion is in 3D. And the black arrows is the basis vector of z-coordinate. And the big red arrow is the normal vector of terrain. And the dotted red line is the projection of the normal vector of terrain in the XOZ plane. I think I should make an example of this projection. Maybe like this. Now here, suppose this is the normal vector of terrain. And you see the projection. Projection? Okay. And now we do our rotation in 3D. And we view this 3D rotation as a combine of two sets of 2D rotation. The first one is we fix the y-axis and rotate it until the z-axis in line with the projection. So we got the x1, y1, z1 coordinate in blue color. Then we do the second rotation. We fix the x1 axis, and then we rotate it until the z1 axis in line with the normal vector of terrain. Then we got the blue pairs of basis vectors, which is what we need. And after the 2D rotation, there are two rotation angles. And use these angles, we can resolve the basis vectors after the 3D rotation we do in last slide. Here is the expression. And to satisfy the vertical distribution of the basis vector of the classic sigma coordinate, we add rotation parameters. So we set the rotation parameters b as 1 on the surface of terrain and 0 on the top of model, just here. So we got the basis vectors of our new coordinate. Here is the expression. Then we draw a picture of it in 2D. Black line is the terrain, and the color arrows are the basis vectors of our orthogonal sigma coordinate. We can see that near the terrain, all the vectors are terrain following, and in all the domain, they are orthogonal. Here we got the orthogonal basis vectors. So the first part is done. And how to do with the second one is to choose the rotation parameters. Here is an example. We choose 3 kinds of the rotation parameters as this 3 expression. And the difference with them is how fast the rotation parameters b decrease while the height z increase. And the right figure is the sigma levels solved by these different rotation parameters. We can see the black one. Black one is the sigma levels of the classic sigma coordinate, and the color one is we use the 3 rotation parameters. You can see that near the steep terrain, we can get smoother sigma levels in high region. And second part is done. Now we're going to resolve the equation of this new coordinate. That is to use the basis vectors we have just got of the sigma coordinate, orthogonal sigma coordinate, to expand the vector equation of the atmosphere. Then we can get the scalar equation of this new coordinate. Here we compare the momentum equation in the orthogonal sigma coordinate and the classic one. We can see the pressure, the expression of the PGF is 1 term, and compared with the 2 terms of the classic one. And there's non-curvilinear term this time. That is to say, our equations in the orthogonal sigma coordinate is as simple as those in the z-coordinate. And we use this simplicity can propose a unified framework to combine the equations in the three coordinates: z-coordinate, classic sigma coordinate, as well as the orthogonal one. Here we use the horizontal momentum equation as an example. We add these three parameters and value them separately in these three coordinates. And when this scalar component of a scalar component is different in each coordinate, like the u, v, w, we use a matrix to transform their values. So we got the unified framework of these three coordinates. Now let's see a short summary of this orthogonal sigma coordinate. First, we use a revised way of the classic sigma coordinate, which is to design the basis vectors firstly and then the definition of coordinate. We can get an orthogonal sigma coordinate. And through rotating the basis vectors of z coordinate, we can get a terrain following and orthogonal basis vectors of our new coordinate. And based on these characteristics, there are three advantages in the new coordinate. First one is we got a one-term computational form of PGF. And the second, we can choose appropriate rotation parameters to obtain the smoother level, sigma levels above steep terrain. And thirdly, our scalar equations in the new coordinate is as simple as those in the z-coordinate, indicating that it's easier to use the equation in a numerical model. Then, how our new coordinate will do a better job than the classic one? To test this, we have done some idealized experiments. And for the PGF errors, since in this coordinate we have one-term computational form, so the results should be similar as the experiments we have done in this paper. So details you can find in this paper and this address. We just omit this part. Now let's see how about the advection errors. We have done some idealized advection experiments, and we use the unified framework just proposed last a few slides ago, and implement the sigma coordinate and the orthogonal one in a unified equation. And here are four groups of the two coordinates. And the one is classic sigma coordinate, and the other three are all the orthogonal sigma coordinate with different rotation parameters we have mentioned earlier. And in each group of the experiments, we have done three different horizontal resolution experiments. So there are 20 experiments. We do the advection experiments in a two-dimension, the vertical section. And it's a linear advection. We put a bell-shaped mountain in the middle of the domain. And here is the analytical solution of this linear advection. The analytical solution is the color counter is the anomaly field. It should flow over the mountain from the left to the right and without changing this shape. And after discretization this equation, we can compute the computational solution in each coordinate. And we compare the computational solution in each coordinate with the analytical one. We got the advection errors and then compared errors. So here we begin our comparison. First is the comparison of the pattern of the advection. We choose two moments. The one is the advection flow over the top of the terrain, and the other is at the end of the process. Here, the first figure is the results obtained by the classic sigma coordinate. We can see on the top of the when it flow over the top of the terrain, there is a huge deformation, and in the orthogonal sigma coordinate, this deformation is alleviated. We calculate the root mean square error of this moment, and we can see the root mean square error are all less than than those in the classic sigma coordinate. Especially when we use the exponent rotation parameters, we can the root mean square error is almost half of this one. And then we compare the advection errors in the whole advection process. Here's the variation of this. We can see that in the whole advection, the advection errors of the orthogonal sigma coordinate is always less than those in the classic sigma errors. Again, when we use the component rotation parameters, the errors are 2 orders of magnitude less than those in the classic sigma coordinate. So here comes a question: what has improved the performance? We analyze this question, use the vertical velocity, and in this linear advection, the choose of the w should be 0, and here is the velocity, vertical velocity we got in each coordinate. We can see that the spurious vertical velocity in the orthogonal sigma coordinate are all less than this one, and especially this when we use the exponent rotation parameters, the vertical velocity is 1 order of magnitude less than this one. Here, the result is consistent with the comparison we have done in last 2 slides. Finally, we compare the root mean square error in all the experiments. If the horizontal axis is the increasing horizontal resolution, and we can see in all the experiments, here 3 figures are the results obtained by the orthogonal sigma coordinate. They're all less than this one. And again, especially use the exponent rotation parameters. In the high resolution, the root mean square error is 1 order of magnitude less than this one. Okay, we have introduced orthogonal terrain-following coordinate, and as well as the associated idealized experiments. Here comes the conclusion. We design an orthogonal sigma coordinate to overcome 2 computation errors in the classic sigma coordinate. In designing this coordinate, we use orthogonal basis vectors to obtain the one-term computational form of PGF so as to bypass these errors. And we add in rotation parameters to decrease the slope of sigma levels, and we alleviate the advection errors in this new coordinate. In our idealized advection experiments, 3. Okay, that's the last page. The advection errors in the orthogonal sigma coordinate is reduced by at least 1 order of magnitude than those in the classic one. And especially in the higher resolution, our new coordinate, the errors in the new coordinate decreased more significantly. And in addition, we choose, if we choose appropriate rotation parameters in the new coordinate, the advection errors can be reduced much more. And that's all about the story. And upon request, I need to say happy birthday to a friend of mine while the camera is rolling. In return, her birthday wishes is for everybody like my new coordinate. Okay? Thank you.
Questions, comments?
Did you compare the reduction of advection errors you can achieve with your new coordinate with appropriate rotation parameters with the reduction one can achieve with the sleeve coordinate with comparable smoothing of the terrain of the coordinate surfaces?
You mean just use another kind of terrain?
No, I mean the sleeve coordinate proposed by Christoph Scher in 2002 or 3. I mean, comparing that with this with the conventional terrain-following coordinate is well a bit unfair because.
Oh, you mean I should compare this with a hybrid one?
Yes. So when you're using a comparable optimization for the standard terrain-following coordinate, you get probably a similar or a bit less improvement, but that would be a more fair comparison than.
I should do that. Yeah. Okay. And
So in those experiments, you didn't show what the coordinate surfaces, but was it just the basic terrain following with the terrain influence decreasing linearly with height in all those experiments? Because you had that BR 1, 2, 3.
We use the rotation parameters as showed before. These are the two. These are 3 expression of the
Oh, okay.
and reuse this in the idealized advection.
So in the green ones, there is no terrain at the level that you're advecting, which is sort of
Yes, because
like
this
a
is
hybrid or like the sleeve would do. So there should be no error at all because there's no terrain influence, or there's no.
and so the result is the same as when we use the hybrid one. But we can do this in this coordinate, and I think that is maybe something like automatically hybrid.
On the slide number 12, you showed the coordinates, and usually with finite difference schemes, you can see there's an equivalence between a finite difference formulation and a finite volume formulation where you've got grid boxes and fluxes between the grid boxes and the coordinate system. And with that, the coordinate system can no longer be viewed as the velocity along the coordinate directions no longer be viewed as fluxes in between non-overlapping grid boxes. And I'm wondering if that has an implication for conservation.
Conservation. I think I should propose the matrix transformation matrix again. Everything is transformed by that matrix. So for the conservation, they can do conservation in the physical space, and here is the computational space. So I think I should go back to that transformation. I mean this one. So everything is transformed in every coordinate. So you want to do things in any coordinate, it's okay. Just use this one. So maybe it's no.
Just follow up the comment on the conservation. I think this idea is similar to our 3D finite volume model, which we construct the 3D finite volume and use our basic normal factor. So my question to you is, your normal factors is perpendicular to your model, to your Turin surface, right?
Yeah.
So if you use four size grid, for example, or ICOS grid, it will not sit on the same plane. The model space grid will not sit on your terrain because only 3 points you need to define the surface. So it even more than 4 points. So my question is, do you thinking about this your basis
Vector.
shape? Right. Basis factor is always normal to your shape. So is your shape what shape is your which shape of your grid sit on top of topography? That's my question. What is the shape of your grid sit on top of?
Oh, you see, what is the computational mesh, right?
Right.
Okay. A good question. Just omit this because the limited time. Here is the red line is the sigma levels, and the blue line is the new x direction. Sorry, it's the x coordinate line. Yeah. So here is the computational space, and but we view it in the physical space. So you see that this is not regular grid, but when we do the transformation, and then in this one, the red dot is the computational grid. It's regular, and the circle, the dark circle, is the point in the physical space. So when we use this coordinate, the computational grid is regular, and I don't know if this answers the question.
Yeah. So basically, you construct your grid box in a terrain.
Yeah. The computational mesh is
on
the
a regular
same.
shape, a regular mesh.
Yeah, regular mesh. It's important for the parameterization. I think we should do this.
Sorry. Well, if you go back to that previous slide you showed, you've now got a huge CFL criterion, a high time step restriction.
Yes, I think about that. I think no, because you see, it's high resolution here, but there's a transformation. The component of the velocity is different. So it's transform that, and I think the CFL, the criterion is the same. I think about that.
I now see how they're not overlapping in that picture.
But we are going to have to move along. I did want to just make one comment that I made at your last presentation. That is that there's no completely free lunch here. And that even though in your orthogonal coordinate system you only have one pressure gradient term, you now also have a gravity term.
Yes.
And that gravity term is exactly the same as the second term that you get if you stay in a regular sigma coordinate, because that G term is essentially dPdz. So you've got, there still is this compensation of two large terms, even in your orthogonal system.
Yes.
So,
Thank you very much. Okay.
let's move along.